In this video, I'll discuss the sources and properties of electromagnetic waves. Let's start with the sources. Basically, there are three sources of electromagnetic waves. This will be a very brief description of each. More detail on some of these will be provided in a later module. So the first one I want to mention is atomic energy transitions. So basically, this means electrons that are dropping down in atomic energy levels. So just to give you the basic idea, if we have an atom where this is the nucleus, then the electrons exist in specific energy levels, which I'll just show this way. So normally electrons exist in the lowest available energy level. So say there's an electron down here, and then if the electrons are energized, they may move up to higher energy levels, say up here. But they will ultimately fall back to the lower energy levels, say here or here. And when they do that, they give off the difference in the energy levels as electromagnetic waves. So that's the gist of that one. The next one I'll mention is nuclear decay, otherwise known as radioactive decay. And so just as an example, say we have uranium-238, which has an atomic number of 92. And so uranium-238 is unstable, and it will naturally decay into helium-4 and thorium-234. And in so doing, some energy is also given off as electromagnetic waves. And then the third method is accelerating charges. And so as you know, we can have linear acceleration where the speed of an object changes, and we can have angular acceleration when an object curves. So as an example of linear acceleration, we can look at a radio broadcasting antenna. Basically, an antenna is just a metal conductor, so it's full of electrons that can move along the antenna. And so if a voltage and therefore an electric field is applied along the antenna, then the electrons can be accelerated. So we might have an AC voltage accelerating the electrons up and down the antenna like this. And as the electrons are accelerated, they give off electromagnetic waves. And so the other way to accelerate is to make it curve. And so a common way to do this is to have the charge moving through a magnetic field. And as it curves, it gives off electromagnetic waves. Okay, so that's basically where electromagnetic waves come from. Now let's talk about the properties of electromagnetic waves. Let's start by seeing what they look like. Basically, electromagnetic waves are electric fields and magnetic fields coupled together as shown in this image. So this wave might have been formed by an accelerating charge over here on the left side, and then the electromagnetic wave propagates away from the source. So this would be the direction of the wave's propagation. And so it will have some speed as it propagates. Let's call it v. And so while it propagates to the right like that, we can see that the electric field, which is the red sine wave, is propagating vertically. And then the magnetic field, which is the blue sine wave, is propagating horizontally. And so you might be able to tell in the image that all three of these vectors, the E field, the B field, and the velocity vector, are all perpendicular to each other. And so you might assign each of these vectors to a coordinate axis, like this. Just as the coordinate axes x, y, and z all have a specific relationship to each other, E, B, and V also have a specific relationship to each other in addition to being perpendicular. And the relationship is defined by a right-hand rule that we'll call right-hand rule number 3. So the steps are: point the fingers of your right hand in the direction of the electric field, then rotate your hand so that you can bend your fingers into the direction of the B field, and then extend your thumb, and it points in the direction of the propagation speed v. So for now, I'll just state these steps, and then we'll practice them in class. The next property I want to mention is that all electromagnetic waves propagate at a speed of 3 × 10⁸ meters per second in a vacuum. So 3 × 10⁸ is the speed of light, and we give it the symbol c. And so this holds true for all electromagnetic waves at any frequency when the waves are in a vacuum. If they're not in a vacuum, then they propagate at a slower speed. So whether that's through glass or a wall, or water, or any object at all. When electromagnetic waves are in air, they do slow down, but by a very small amount. So we will approximate that light, or electromagnetic waves, travel at 3 times 10 to the 8 meters per second in air as well. Okay, so the next rule is that electromagnetic waves are transverse waves. And so you may recall that transverse waves means that the disturbance is perpendicular to the direction of propagation. So if we look back up at the figure, then the disturbances are the electric and magnetic fields, which are going in the y direction and the z direction, which are both perpendicular to the direction of propagation, which I've shown to be in the x direction. Okay, so the next property I've already implied, and that is that electromagnetic waves do not require a medium. So in other words, they can propagate in a medium or in a vacuum. Most waves, like sound waves, require a medium. So the next property actually applies to any type of wave. So this is an equation that relates the speed of propagation to the frequency and the wavelength of the wave. So v is the speed of propagation, f is the frequency in hertz, and lambda is the wavelength. And so in the last video, we recognized that the frequency and the wavelength of a wave were inversely proportional to each other. In other words, if we had a wave like a radio wave with a very low frequency, then it had a large wavelength. And so since the speed of propagation would be the speed of light, which is basically constant, then we can see that the frequency and the wavelength must be inversely proportional per this equation. Then another equation relates the magnitudes of the electric field and magnetic field. So E is the magnitude of the electric field, B is the magnitude of the B field, and C is the speed of light, 3 times 10 to the 8 meters per second. And so this relationship will hold at any instant. Even though the electric field and the magnetic field are sinusoidal, at any instant, the values of each will obey this relationship. And then the last property is just a general statement. When electromagnetic waves are incident on matter, in other words, they come in contact with a medium, water, a brick wall, whatever, they may be reflected and or be absorbed and or be transmitted through, meaning pass through the medium. Which one of these happens, which combination of these happens, depends on the frequency of the electromagnetic wave and on the properties of the matter that it interacts with. We won't get into the details of determining why one happens versus the other. We just need to know in general that this is the case. All right, so that's the end of this video on the sources of electromagnetic waves and the properties of them.